In this lecture, we're going to take a look at how to do definite integrals using this integration by parts technique. And you really do it pretty much, I think, the way your intuition probably tells you that you should. You evaluate the UV part from A to B, and you evaluate the integral part exactly the way you would normally do an integral. So essentially, in practice, what I'm going to do is I'm going to completely evaluate that right-hand side, including the integral. Then I'm just going to put big parentheses around it and evaluate the whole thing from A to B. So I've got some examples here, right? Take a look. This is kind of a basic one to start off with. So I'm going to use our integration by parts method. You see that this kind of has the setup that we look for. We have two functions, theta and cosine of theta, being multiplied together. That's a good indicator that we should give integration by parts a try. And I'm going to let u equal theta, right? Because I'm thinking then when I do the differentiation part, du equals d theta, and the variable just goes away, which is usually a good thing. Then over here, I'm going to let dv equal cosine theta d theta. And if we integrate both sides of this, v is equal to sine theta. All right, good. So now I'm going to do the integral. Our integration by parts formula says that this is equal to uv, that's theta sine theta, minus the integral of v du. So that's sine theta d theta. See, that was a good choice for the u part because it eliminated that term that was kind of causing us trouble from the original integral. Now, if we're thinking about the bounds, this is from 0 to pi, and this is from 0 to pi. Right now, I'm actually not going to try to evaluate that part. I'm just going to leave that part like it is. This is theta sine theta. I'm going to do the integral. The integral of sine theta is negative cosine theta. So I've got this minus sign out in front. So this is going to become plus cosine theta. And then I'm just going to do the whole thing from 0 to pi. All right, so if we put pi in here, this is pi sine of pi plus cosine of pi minus 0 times the sine of 0 plus the cosine of 0. All right, so what do we get here? Sine of pi is 0, so that term goes away. Cosine of pi is negative 1. And what do we get over here? This is minus, that part's just 0. Cosine of 0 is 1. So this whole integral evaluates to negative 2. Okay, how about this one? This one is actually kind of interesting, right? And an interesting thing is gonna happen when we try to use our integration by parts method here. Right, so for the time being, I'm going to ignore the 0 to 2 part, right, and just focus on finding the antiderivative here, right? Then we'll bring the 0 to 2 back and do the evaluation part. So what I'm going to do here is I'm going to let u equal e to the x and dv equal cosine of x dx. All right, now see, this is going to be a little interesting. Du equals e to the x dx, and it really didn't go away. So then this part, we integrate v equals the sine of x. All right, so what did that do? Well, I'm really going to write this thing out. There's a reason why I'm writing the whole thing out, right? So just kind of bear with me. The integral, I said I'm not going to put the bounds, right? Let's just do the integral for now. We'll add the bounds back in at the end. E to the x cosine of x dx is uv, that's e to the x sine of x, minus the integral, right, that was this part. Now we're going to do v du, that's e to the x sine of x dx. Now, at first glance, I mean, you're maybe looking at this and saying, well, that really didn't help me any. I just traded one trig function for another. But, and this is where there's an interesting little twist here. Remember, the derivatives of the sine and cosine, they're kind of cyclic, right? You start with a cosine, you take the derivative, you get the sine, give or take a negative sign. Then you take the derivative again, and you're back to the cosine. I'm going to take advantage of that here to get this integral. So what I'm going to do here, I'm going to do integration by parts again. I'm going to let u equal e to the x again. So du equals e to the x dx. Then I'm going to let dv equals sine of x dx. So v is, careful with the signs here, negative cosine of x. All right, now let's do this again. This is, and I'm actually going to scoot this over a little bit. This is integral e to the x cosine of x dx equals e to the x sine of x. And now let's be real careful with this minus sign. We're going to group this here. We're going to do u v, so that's minus e to the x cosine of x. Then I'm going to do minus the integral of v du, and that's minus cosine of x, so the minuses are going to cancel, and this will be plus the integral of e to the x cosine of x dx. Close those. Now, this is equal to e to the x sine of x plus e to the x cosine of x minus, and I can do this integral now. This is e to the x sine of x. Well, excuse me, that is not what that integral is. What was I thinking? This is minus the integral of e to the x cosine of x dx. We don't know what it is, right? That actually is what we're trying to find, and this is where this gets interesting. Let me write this in here: e to the x cosine of x dx. Now notice that I have this here on both sides. All right, so what I'm going to do is I'm going to add it to both sides. And this is going to become 2 integral e to the x cosine of x dx equals e to the x sine of x plus e to the x cosine of x. And now if I divide by 2, I have my integral. The integral of e to the x cosine of x is 1/2 e to the x sine of x plus e to the x cosine of x, and I'm done. Well, I'm not done. I got to do the 0 to 2 part. But before we do that, right, I want you to take a step back and see what happened here, right? Because I had something in here that had whose derivatives have kind of a cyclic nature, right? They alternate back and forth between cosine and sine, give or take a negative. I was able to take advantage of that and just do this twice, right? Thinking, okay, I'm going to end up back where I started, and then I can just do this bit where I add it to both sides. All right, so now let's get the numbers in here. I'm going to do this from 0 to 2. I'm going to do this from 0 to 2. And let's see, this is 1/2 e squared sine of 2 plus e squared cosine of 2 minus e to the 0 sine of 0 minus e to the 0 cosine of 0. Okay, sine of 0 is just 0, so this part goes away. Cosine of 0 is 1, so this whole thing is a very weird number. 1/2 e squared sine of 2 plus e squared cosine of 2 minus 1, right? E to the 0 is also 1, so that whole term is 1. And that's it, right? Now, really kind of a weird result, right? And not like some of the really nice numbers we've been lucky to get so far. But that's our answer, right? That's what this integral evaluates to. Okay, so this brings us to the end of our discussion of integration by parts. And in the next lecture, we're going to start kind of a new section talking about integrals involving trigonometric functions.